In this video, we are going to look at how second-order differential equations can be used to solve a pair of simultaneous first-order differential equations. And this is a topic in Unit 4 of the WJEC Further Mathematics specification. The specification says that if we have one independent variable, that is t, and two variables x and y, which depend on t, and the variables x, y and t are linked by a pair of simultaneous equations which are actually differential equations of the form dx by dt equals ax plus by plus ft plus a function of t, and dy by dt equals cx plus dy plus a second function of t, that is g of t, then we should be able to solve that sort of equation. The process for solving equations of this format is to set up a second order differential equation, either linking x and t with no mention of y, or linking y and t with no mention of x. To set up the second order differential equation that links x and t with no mention of y, we start by differentiating the first equation to obtain d2x dt squared plus a dx by dt plus b dy by dt plus the derivative of f. Then we substitute for dy by dt using equation 2. So the term b dy by dt in equation 3 becomes b times cx plus dy plus gt. Finally, we use equation 1 and make y the subject of equation 1, and then substitute for y in equation 4. Once we've done that, we will need to simplify the result quite dramatically. So let's now have a look at this in practice. So we have the simultaneous equations dx by dt equals 4x minus 6y minus 9 sine t, dy by dt equals 3x minus 5y minus 7 sine t to be solved. And first of all, it asks me to show that d2x dt squared plus dx by dt minus 2x must equal minus 9 cos t minus 3 sine t. So we'll start by just labelling off the two equations. If we differentiate equation 1, we will obtain an equation involving d2x dt squared. So, differentiating equation 1, I get d2x dt squared is 4 dx by dt minus 6 dy by dt minus 9 cos t. Having got that, I can now substitute for dy by dt and obtain d2x dt squared equals 4 dx by dt minus 6 lots of 3x minus 5y minus 7 sine t minus 9 cos t. If we tidy that up a little bit, multiply the brackets out, we've got d2x dt squared is 4 dx by dt minus 18x plus 30y minus plus 42 sine t minus 9 cos t. Now we still need to get rid of the y's in this expression. Okay, and we can do that by rearranging equation 1 to make y the subject of the formula. So if I rearrange equation 1 to make y the subject, then I've got 6y is equal to 4x minus 9 sine t minus dx by dt. In other words, y is 1/6 of 4x minus 9 sine t minus dx by dt. So if I now substitute this into my equation 4, I've now got d2x dt squared equals 4dx by dt minus 18x plus 30 times by 1/6 4x minus 9 sine t minus dx by dt plus then the 42 sine t minus the 9 cos t. Tidying that up, we've got d2x dt squared is 4 dx by dt minus 18x plus 20x. Now that comes from the 5 times 4x that we've got, so 30 times the 6th is 5, times by 4x gives me the 20x. Then I've got minus 5 lots of 9 sine t, so that's minus 45 sine t. And then I've got minus 5 lots of dx by dt, and I've still got the plus 42 sine t minus 9 cos t. So we've now got d2x dt squared equals minus dx by dt plus 2x minus 3 sine t minus 9 cos t. In other words, d2x dt squared plus dx by dt minus 2x equals minus 9 cos t minus 3 sine t. So we can now find the general solution for x. So as before, we're going to have to find a complementary function and a particular integral. The complementary function, we're trying to solve d2x dt squared plus dx by dt minus 2x equals 0. The auxiliary equation is k squared plus k minus 2 equals 0, which gives me k equals 1 or k equals minus 2. So the complementary function is x equals a e to the t plus b e to the minus 2t. Looking at the right-hand side of our differential equation, we can see that we have minus 9 cos t minus 3 sin t, so it would seem perfectly sensible to try and find a particular integral of the form alpha times cos t plus beta times sin t. In which case, dx by dt will be minus alpha sin t plus beta cos t, and d2x dt squared will be minus alpha cos t minus beta sin t. So d2x dt squared plus dx by dt minus 2x will be minus alpha cos t minus beta sin t plus minus alpha sin t plus beta cos t minus 2 lots of alpha cos t plus beta sin t. If you look at the cos t terms first of all, from the first bracket we've got minus alpha, from the second bracket we've got beta, and from the third bracket we've got another minus 2 alpha. So we've got minus 3 alpha plus beta, lots of cos t. And then if we look at the sin t terms, we've got minus beta from the first bracket, minus alpha from the second bracket, and minus 2 beta from the third bracket. So we've got minus 3 beta minus alpha lots of sine t. Now we want this to equal minus 9 cos t minus 3 sine t. So we need minus 3 alpha plus beta equals minus 9, and minus 3 beta minus alpha to equal minus 3. The solution of that pair of simultaneous equations is alpha equals 3 and beta equals 0. So we have a particular integral of x equals 3 cos t. So our general solution is x equals 3 cos t plus a e to the t plus b e to the minus 2t. So we've now got to find the general solution for y as well. Well, we've already worked out earlier on that y is the same thing as 1/6 of 4x minus 9 sine t minus dx by dt. So we've got y is 1/6 of 4x, so that's 12 cos t plus 4a e to the t plus 4b e to the minus 2t. Take away 9 sine t. Take away dx by dt. Well, dx by dt is minus 3 sine t plus a e to the t minus 2b e to the minus 2t. So there's a bit of tidying up that needs to be done there. So that gives me 1/6 of 12 cos t plus 3a e to the t plus 6b e to the minus 2t minus 6 sine t. In other words, 2 cos t minus sine t plus a half a e to the t plus b e to the minus 2t. Now we're now told that x is bounded as t tends to infinity. Well, if we look at the different terms in x, 3 cos t always lies between 3 and minus 3. A e to the t is going to tend to infinity if a is anything other than 0. b e to the minus 2t tends to 0 as t tends to infinity. So if x is bounded as t tends to infinity, we must have a equals 0. And we can see that if x is bounded, and looking at the expression for y, then cos t is bounded, 2 cos t is bounded between 2 and minus 2. Sine t is bounded between 1 and minus 1. There's no e to the t term because a is equal to 0. And e to the minus 2t tends to 0 as t tends to infinity. So if x is bounded, then y is also going to be bounded. Now finally, we've got y equals 0 when t equals 0. So we've got to now find the particular solutions for x and y. So when t equals 0, y equals 0 tells me that I've got 0 equals 2 minus 0 plus b. In other words, b must be minus 2. And if b equals minus 2, then that now means that I've got x equals 3 cos t minus 2e to the minus 2t, and y is 2 cos t minus sine t minus 2e to the minus 2t. As t tends to infinity, e to the minus 2t gets smaller and smaller. So as t tends to infinity, x gets closer and closer to 3 cos t, and y gets closer and closer to 2 cos t minus sine t.